Today we have Stefano Poli, and I am sure that any of you who study subduction zones know many, many papers by Poli and Schmidt and Schmidt and Poli and Poli and Schmidt about what happens into water in subduction zones. Anyway, he flew in from, I guess, Italy yesterday or the day before? Saturday. No jet lag. Anyway, Stefano got his PhD from University of Milan, and not too far long ago, I think. And then went to Zurich and worked with Peter Ulmer and Max Schmidt as a postdoc and developed, I guess, some of the experimental facilities that they have there. And then returned to Milan, where he has been ever since. He tells me interesting stories about trying to be a volcanologist in Italy, and it was very, very difficult because apparently the Italian establishment is a very difficult bunch of people to deal with, so he's no longer a volcanologist. Anyway, today he's going to speak about carbonatites in subduction zones, both from experimental point of view and from natural observations. And on that note,
okay. So, thank you, Björn. So, thank you for the kind invitation. It's an honor to be here. Thank you for the opportunity to show you some results we obtained recently on a system where the amount of work was, originally in experimental petrology, sort of cutting edge in 60 years ago or 70 years ago or even a few hundred years ago. But nowadays, this kind of system is probably somewhat under-evaluated, and we are doing new experiments in this simple system. So I would like to thank my PhD students, postdocs, and collaborators, Erwin Schettino, Sutao Zhao, Fabio Ferri, Michele Rinaldi, and Andres Rodriguez Vargas in Colombia for the nice natural example I'm going to show you in the latest part of my presentation. So you probably know that carbonatite magmas are in almost 100% of the cases are located in anorogenic tectonic environments. So they are located either in extensional regime or in cratonic areas. And basically, we have no clear examples at convergent margins. There is maybe a locality not confirmed here in Kamchatka, and probably the only place where you are in a sort of orogenic setting is in Italy. And there was this paper, controversial paper, with this entitled Carbonatite subduction system. These are calcic carbonatites. They are located in a sort of back arc position compared to the volcanic arc in central Italy. But they are a very interesting case because, in general, Italy, as observed from the space, is for sure is located in on a convergent margin. And if you are not familiar with carbonatitic magmas, the field here represented by this review paper by Hamoud and Keshav a couple of years ago, you can see that the composition of carbonatites is usually dolomitic, and there is quite a bunch of calcic carbonatites, and there is a considerable debate about the origin of calcic carbonatites, if they are the result of differentiation or if it's possible to produce them directly from a mantle source or from some process involving the reaction between a primary dolomitic magma and the Harzburgite, a hosting Harzburgite when the carbonatite liquid upwell to the surface. And in this figure, you can see the composition of the synthetic analogues. So since many tens of years, experimental petrologists are trying to reproduce the composition of of these carbonatitic magmas, either starting from a peridotite, a carbonated peridotite, or from a basaltic eclogite, a carbonated basaltic eclogite. And as you can see here, basically the experimental results point to grossly dolomitic composition when you have a carbonated peridotite, and somewhat more calcic composition, but not really true calcic carbonatites. And these points here have some special feature, and I will discuss that later on. Obviously, to produce this kind of magma, you need a carbonated rock at mantle pressure. And so subduction systems are the ideal environment to refertilize, to recycle carbonate to depth. And so if you have an ultramafic rock on the ocean floor, by means of we know this is also used as a construction stone building, and we see that this network of veins are composed mainly of carbonates. Usually they are calcium carbonate, or in cases also magnesite. And then on subduction and metamorphism, you can generate in ophiolitic terrain this kind of serpentinites with rhodingites, or in any case layer of carbonates where you can observe 2 or 3 carbonates, for instance here, calcite, dolomite, magnesite, as you move from the regional vein to the serpentinized matrix. And then this is entrapped in the cycle, in the petrogenetic cycle at subduction zone. Can form so when this dehydrate and you move to the mantle wedge, you can generate this kind of peridotite. This is the very famous garnet peridotite from Bardane, where inside garnet you observe orthopyroxene, which hosts inclusions with magnesite and diamond and some hydrous phases. So we know that there is a cycle for carbon, and carbonates can occur in the wedge and in the mantle at diamond pressure, at high pressure. So the same is true for basaltic eclogites. So basically we start from the so-called altered oceanic crust. The altered oceanic crust is a sort of breccia where you can see again a network of veins with carbonates, and again upon metamorphism, high pressure metamorphism, you generate eclogites, and these eclogites can contain again magnesite, dolomite, and especially dolomite can conserve a lot of information, because the growth rate of dolomite is much lower than, and the diffusion rate of most cations is much lower in dolomite than in other carbonates, so it can record a lot of the metamorphic history of these rocks. But I would like to stress that at high pressure, in the mantle, at mantle pressure, we don't have only magnesite and dolomite. There is also calcite. Calcite is quite important because in large areas on the ocean floor, you have hundreds of meter thick sequences of pelagic limestones, and these limestones are basically composed of calcium carbonate. These are the famous White Cliffs of Dover, and they are oceanic chalk. And if we look at this kind of sequences, they can be, for instance, here in the DSDP site 212 in the Indian Ocean out of Java subduction zone. Probably you cannot see the numbers here, but this is 500 meters. So here you have 500 meters of this symbol, and this symbol corresponds, here is written nanos, so nanoconids, clay and mica. And the number here is 96%. So, and these guys here, this biomineralization, composed of ultra pure calcite. okay? So it means that apart from some minor content in clay, these 100 meters thick sequences, packs, are composed of calcite. So on subduction, you actually, so what you generate a marble, more or less impure marbles. It depends on the amount of impurities you have in the original limestones, and eventually you can get something like that. So a calcite schist with some micas or chloride plus calcite in this layer. So it's very important to stress the point that there is an intrinsic difference between carbonates and hydrous phases. This is very simplistic, but it shows a fundamental difference behind the behavior of carbonates compared to hydrous phases. So we know since long time that dehydration is a common feature of hydrated lithologies upon progressive metamorphism. And so we can describe this dehydration by comparing the chemical potential of H2O as buffered by an assemblage bearing an hydrous phase. For instance, if we have an assemblage with antigorite, forsterite, and denstatite, this assemblage buffer the chemical potential of H2O as a component at this condition. So we can compute this easily with a routine equation of state for water. Okay. So on this side, in this block diagram, we have a temperature increasing in this direction, pressure increasing in this direction, and this is the joule of the chemical potential. So on the right, we have the equation of state of the fluid, of a pure fluid, H2O. Similarly, we can compute the chemical potential for CO2 as buffered by a solid assemblage, and the chemical potential of CO2 as buffered by the fluid composed of carbon dioxide. Okay. So as you can see, is that obviously the scale, as we have different compounds, the absolute values are quite different. But if we compare grossly these two surfaces, they are not so different. Okay. So they look more or less parallel. So it means that although they're shifted in absolute values, the pressure and temperature dependence of the chemical potential of H2O and CO2 are, as buffered by the solids, is similar. So we should expect, okay, carbonate and hydrous phase are not so different in behavior in pressure, temperature, space. But the point is that, as you can see here, because of the larger molar volume of CO2 and therefore the partial derivative of the free energy versus pressure. So you see here that this surface is much steeper. The free energy surface for CO2 is much steeper than that of water. So what happens when we intersect these surfaces? We have quite different intersections. Okay, so obviously when the free energy surface is lower, this is the stable phase. This is a stable phase. So obviously here at high temperature, it will be water. I mean, the fluid will be stable. Here, the hydrous phase is stable. And the same for this. Okay, these are is buffered by the carbonates, and this is the CO2. So this represents the decarbonation. This is the dehydration. Okay. So now, if we compare this intersection with a typical PT path for a subducting slab or the hanging wall in the mantle, what we can see is that what we expect is that in general, as a general rule, the dpdt slope for a dehydration reaction is relatively steep. So compared to a typical prograde PT path, sooner or later we get an intersection between the PT path and the intersection which represent the dehydration. On the contrary, because of this different shape of the free energy surface for CO2, usually the dPdT slope is much lower, and so you usually do not intersect the PT path for a subducting slab does not intersect this intersection, which represents the decarbonation. So we would expect for simple system, because of this difference in the equation of state of CO2, for simple system in general, we expect that hydrous phases sooner or later they decompose, whereas carbonates are happy at high pressure, and actually even the melt in some cases you just cannot decarbonate. You just go to melting at 1500, 1600, so they are very stable at high pressure carbonates in very simple system. Okay, and actually, so they survive. They easily survive the subduction process, and then we can find them even in the mantle. In diamonds, for instance, these were proposed, it was proposed that these diamonds from Brazil, from Huina, as far as I remember, these are this diamond contain inclusions of calcium-rich phases, and among these calcium-rich phases you have also calcite. Probably this was formerly an aragonite, possibly, but anyway, it contains calcium-rich phases, and among these phases, calcium-rich phases, you also have a calcium carbonate, and so this testifies to a long history for this kind of material deep in the mantle. So now I think we have three fundamental questions. So why are carbonatitic liquids so unusual at convergence margins, if any? If subduction drives so large quantities of carbonate depth, because we know that, okay, that alteration, hydrothermal metamorphism on the ocean floor add carbonates. Carbonates can survive, so why we do not observe carbonatitic liquids? So now the point is that these kind of liquids are unfeasible subduction zone, or they simply represent batches of magma that we do not expect they can maintain their identity because of reaction with war rock and a long process of ascent, and therefore we expect that metasomatism completely transform this kind of liquid in a different thing in the mantle wedge. So, but another point is that are we really looking for the right carbonatitic component? Because most experimental petrologists focused on three large categories of bulk composition. So obviously carbonated peridotite as an ideal source for carbonatitic magmas, for instance, peridotite plus CO2. This is the solidus where a carbonatitic liquid occur according to work by Dasgupta. Here the so-called carbonatitic ledge is not, I mean, I'm dealing with relatively high pressure conditions, so I won't go into the details of the so-called carbonatitic ledge down here. So as you can see, it goes from approximately 1,000 degrees to 1,200 degrees or 1,300 degrees C at 8 GPa. So you cannot get, I mean, it's obviously for a hanging wall of the subduction slab, or for a material, for a ultramafic material in subducting slab is, I mean, it's very difficult to achieve this kind of condition, so we do not expect carbonatitic liquids from a carbonated peridotite. This is the eclogitic basalt, and as you can see here, obviously is somewhat displaced to lower temperature, but again higher than the 1,000 degrees C, 1,100 degrees C. And then there was a considerable emphasis on metasedimentary material, but not on calcic component, but rather on the so-called carbonaceous, not carbonaceous, I mean carbonated pelite. Why carbonated pelite? Because the so-called gloss, the global subducting sediment, so this kind of average, this average is heavily displaced to heterogeneous contribution. So a heterogeneous contribution means you add aluminum, you add iron, magnesium, and potassium. Okay. So, and actually because of this, the solidus here leads to a potassium-rich carbonatite. And again, maybe, I don't know if you can see here, there should be a sort of gray area. This is the subarc region, so we do not expect, again, that there is an intersection between the subducting path and this solidus in the subarc region. So obviously then if you go deeper, maybe in the transition zone, it is accepted that you can generate this kind of potassium carbonatitic component from metasedimentary material, but not in this more common situation. So I would like then to emphasize again the importance of studying calcite, because as I told you, we have thick piles of pure calcium carbonate that are subducted, I mean, in large areas of active subduction systems. And actually, calcite was very popular. Actually, Sir James Hall performed his first experiments at the beginning of the 19th century on calcite, and even in 1958, Patterson he observed this very nice dendritic growth of calcite when heated at 930 degrees C and 50 bar. Okay, so at 50 bar you are above this invariant point, so you can start melting. Okay, so the anhydrous melting is located approximately at 1300 at this condition, 1250, 1300. And if you add H2O, we interpret this kind of textural feature as a result of quench, okay, of a quench from a liquid. I mean, all experimental petrologists use this kind of textural features to speculate about the original condition of the original state of the material at run condition. So apparently there is even at only 50 bar, there is a major shift in the minimum melting temperature of calcite when in the presence of H2O. So almost actually 50 years ago, Pete Wiley did and Wiley and Bircher, they published a series of papers on this kind of problem, and this is a very nice system. It appears to be relatively simplified, but it's very complex at high pressure and temperature. This is the subsolidus. It's pretty simple. Here you have lime, portlandite, calcite, and the fluid here. So at low pressure, you have the vaporous surface is here. So here is the fluid. And here you have portlandite, here you have calcium carbonate, and this is a maximum thermal divide. And at low pressure, you can see that when you have saturation in H2O, you have the wet eutectic. Here is portlandite, and apparently you move from 1300 down to 650, so a huge difference. And so this huge difference is even more pronounced at high pressure, because apparently, obviously here we have a positive dPdt slope. We have a positive dPdt slope for the anhydrous melting of calcium carbonate, whereas here you have a mildly negative slope. So here, I mean, if this is true, actually, as far as I know, there are not so many attempts to reproduce these experiments, you have more than 1,000 degrees C difference between anhydrous and hydrous melting of calcite. Okay, and this diagram also demonstrates, because of the shape of this, of the position of this cotectic line. Obviously, this also shows clearly that if we I constructed this isothermal diagram from the original diagram of Weil and Böttcher, and this shows, obviously, this is a hypothetical. It's simply a topology. I don't want to claim that this is the exact field. Nobody did that for this system. But it demonstrates that calcium carbon H2O is not a binary. It's not a binary because melt is here. So furthermore, here I neglected the redox reaction. So obviously, as a function of eventually, if you have a buffer for hydrogen or oxygen, this point moves around, and so you need at least 3 components, or 4 components, to describe this system. Okay, and the interesting thing is that it's a very high pressure. Weil and Böttcher, they propose that there is a supercritical so-called second critical point at approximately 4 GPa, and as a result of this second critical point, you lose the physical distinction between what we would call the melt and the fluid. We have a single liquid, but you have a single liquid here, but here you still have 2 liquids. So we should be careful in using this idea of a supercritical liquid, because it strongly depends on the bulk you are looking at. And this diagram, this system, which is relatively simple system, it shows you quite strange features, because here actually, if you move from 1 to 3, you add volatile. Okay, so this is a volatile rich region. This is volatile poor region. Okay, but if we have a point 1 is in the volatile poor region, it has melt, and as you enrich in volatiles, you move then to subsolidus, because this is a fluid. So here in this system, you add volatile and you move from supersolidus to subsolidus condition, which is some sort of counterintuitive. Okay, so and you can also play if you move here and you want to move toward the H2O, that if you want to add only an H2O component. I mean, it depends on the slope of this, but it's not so unrealistic again that you simply add H2O and you move to subsolidus condition. So I mean, it's probably this system is not that relevant for specific application, because in most cases we don't have a system with Portlandite, but the topology is very instructive, because it tells you how complex or how counterintuitive some process can be. So because nobody observed, as far as I know, nobody observed Portlandite as a relevant component, at least in high pressure rocks, I decided to make experiments in a more complex system, where you add aluminum and silica. Actually, in limestone, you always have some silica around. You always have a terrigenous component, which adds that adds at least aluminum. Okay, so if we project in this diagram the composition of pelagic limestones, or for instance of marbles and calcist from the ophiolites, this green field, we can see that obviously they are displaced toward the calcium carbonate, but they're also somewhat saturated in aluminum silicate, which is reasonable, because obviously we have the terrigenous component. And I would like to stress that all of the previous experimental study basically focused, apart from a couple of cases, focused on the so-called gloss composition. So they are much richer in magnesium and iron compared to the kind of sediments I showed you before. So these are the bulk we selected. We were in the range of 750 to 1,000 degrees C, from 4 to 6 GPa with a Walker type multi-anvil. So the amount of fluid is relatively large. I mean, it's pretty large actually, but the idea was also to see, or if you want to verify, if we have two separate fluid and liquid together, or if a single liquid was present at run conditions. So at subsolidus, at the subsolidus, obviously there are two, in this kind of system, there are two minerals that are relevant, two typical metamorphic minerals, zoisite and lawsonite. But zoisite, I mean, is not so typical metamorphic, because you should remember that it can go to 1,200 degrees C. Zoisite has a pretty large stability field, not for lawsonite, but it could be relevant as well. I will show you later, okay? So this is the subsolidus, if you want. And if we go at 800 degrees, actually, this is the region of the capsule where the fluid was present. You see, I mean, a lot of empty space. Empty space means that this is a porosity. If there is a porosity, I assume there was a fluid, what we would call a fluid. So large amount of volatile present in this kind of fluid liquid. I prefer probably to use the term liquid rather than fluid. But so large amount of volatiles. But you see that at 800 degrees, you already have spherulites, globules of both aluminum silica and globules of calcium carbonate, okay? Plus some droplets of silica, some sort of fish egg droplets of pure silica. So there, it's clear that we already have a load of dissolved material in this fluid. If we increase the temperature at 850, it changes, and in the porosity, we see much larger amounts of this kind of fish egg droplets, silica droplets, but we start to have dendrites of carbonates and whiskery crystals. And then at 900 degrees, we definitely have a major change in the textural feature, because we see we clearly have a meniscus in the capsule, and then the typical dendritic growth, which is related to a high load of dissolved material. So, I mean, should we call that a liquid, a fluid? No matter, but it has a very large content of calcium carbonates and of silica. Obviously, the amount of silica depends a lot on the bulk composition we have. Actually, we have these three bulk have different amount of silica, and so as a result, we also have, for instance, in this case, we only have in the meniscus calcium, I mean, chains, dendrites of calcium carbonates and aluminum silica quench products. Whereas if we increase the amount of silica, we also have the appearance of glass, and up to real, I mean, glass with bubbles that, I mean, they appear to be produced by exsolution of the H2O and CO2 on quenching, and in this silicate glass we observe dendrites of calcium carbonate. So by image analysis, by analyzing the quench products, and by image analysis, we can reconstruct the composition of precipitates. So the fish egg droplets are basically pure silica. The glass is enriched in silica, but it has a considerable amount of calcium and aluminum. And for some reason, the whiskers, the whiskers we observe are on the joint silica alumina, but without any calcium. So by image analysis, we can reconstruct the composition of these liquids. The amount of aluminum is relatively low, and I mean, we still don't have a systematic on that, but what we can see in general, obviously, is that, okay, if we are undersaturated in silica, this run head corundum obviously is more enriched in calcium carbonate. As we increase, the yellow one is the bulk composition with the bulk composition with larger amount of silica in the run charge, and obviously is displaced in this direction. But in general, I mean, if I want to find a rule in the or a trend in this point, what I can see is that as we move up in temperature at 50, 900, 950, there is with temperature there in this temperature window, we have an increase in the amount of calcium carbonate that is very sharp. I mean, in this region between 850 and 900, where we observe the formation of what we would call a glass. So I think that, so if we now compare this region between 850, 900, the run charges testify to the presence of high loads, or what we would call probably a hydrous carbonatitic liquid, because of the features of the run charges. We can call that a hydrous carbonatitic liquid that comes from the dissolution, from a dissolution process that in this temperature window becomes more and more effective in the presence of H2O and of an aluminum silicate, which could be, for instance, zoisite or any other kind of aluminum silicate participating to this reaction. And now, if we compare with the PT path for a subduction zone, this is not unrealistic to generate hydrous carbonatitic liquid. So again, the temperature drop is pretty large compared to, for instance, the melting of calcite plus quartz anhydrous. So it's more than 800 degrees C, 800 and 900 degrees C. It's not so extreme as for the case for Portlandite, but I think this is probably more realistic for natural occurrences. So a couple of years ago, I published a paper on a system that is somewhat more complex compared to the example I show you, but basically on the same line of reasoning, in the sense that most people, even myself, we were concerned mostly on a typical basaltic eclogite. So I don't know, magnesium number 50-60, and the normative anorthitic content in the order of 20-30% of normative anorthite. Okay, this is typical for a basalt, for a tholeiitic basalt, because we assume that the so-called altered oceanic crust is basaltic. Okay. However, it's important to remember that below the tholeiites, we have a thick sequence of gabbro, of cumulative gabbro. For instance, here, now I don't remember where this is, maybe in the East Pacific rise. You have here almost, this is depth, meters below sea depth, I think. Anyway, these are almost 1,000 meters of gabbro, where you have a mode, so a volume abundance of plagioclase that goes from 60 to almost 80% of these rocks are composed of plagioclase. They are troctolites. Okay, and if you look at the anorthite content of this plagioclase, the anorthite content is 80. So these gabbroic rocks are extremely enriched in normative anorthite content. So they are extremely rich in calcium compared, in calcium and aluminum compared to a normal basalt. Okay. So I performed experiments again in this region And so in the subsolidus, I show you this map, this diagram, because it shows you basically at this condition, you actually, as expected, you can have epidote present, obviously again with an aluminum silicate plus carbonates. Obviously you have dolomite, you don't have calcite because it's basalt, it's not so extreme composition compared to a pelagic limestone. So you have dolomite plus some, eventually some magnesite. And again, in this similar temperature region, we observe this kind of textural features. We see these lobe and cusp structures, and if we that might suggest the occurrence of a liquid. And if we then increase, if we try to do sandwich experiments where we increase the amount of the putative liquid in the run charge, we actually see a true feature, a textural feature that most experimental petrologists interpret as a result of precipitation from a quenched liquid, precipitation from a liquid. So typical dendritic growth of, in this case, of carbonates in a foam of silicate glass. And when we have these tiny bubbles, usually experimental petrologists assume that the exsolution process underwent during quenching and not at run condition. When fluid is present in run condition, usually in this kind of liquids, it tends to form big, relatively big bubbles of several tens of micrometers, and eventually even only 2 or 3 big bubbles. Because of the relatively low viscosity when carbonates are dissolved in the liquid. Okay, so and the composition of the liquids we could analyze and again reconstruct by by combining, for instance, a large diameter beam with a microprobe, or by image analysis. The composition of the liquids is up there. So these are carbonatitic liquids that are quite enriched in calcium carbonate, and they actually superpose to the composition of 2 other liquids previously obtained, for instance, by Tara Muda and Katie Kiseva. And these 2 studies had some H2O inside. Compared to the other experiments performed by other authors, which were claimed to be anhydrous. And the nice point is that if we compare the composition of these liquids to the composition of the expected carbonate, not carbonate liquid, but carbonate solid at this temperature, they lie very close to this point. Okay, so here, this is the phase diagram for ternary carbonates. So this is one phase field, 1 phase field, 2 phase field, 2 phase field. Here you have a 3-phase field. And so if we compare this topology, is actually very similar to what we have in feldspars. In feldspars, we have a cotectic line where you precipitate 2 feldspars together, and there is a cotectic line with a critical endpoint when you lose the identity between the two feldspars. Okay, so I don't have the time to go into the detail of this, but it's not that unusual for rocks. It resembles a lot the topology for feldspars. Okay, so it's possible that at such condition we can precipitate both I mean a calcium carbonate and a dolomite from this kind of liquid. So when we compare to anhydrous compositions that are down here, this is the dry minimum. Okay, this is the dry peritectic, so in the system, and we see that actually the composition of the liquid from the carbonatitic liquid from the study of the Axel Brau, Das Gupta, they are pretty close to where the cotectic and the peritectic likely lie on the basis of the experiments in the binary system. But now, what is interesting is, again, to go back to the phase diagram proposed by Ellis and Wiley, because I showed you before that, for instance, at 2.5 GPa, this is the melting of calcium carbonate, anhydrous is 1400, hydrous is 660. Again, as I told you before, a huge difference, okay? No, 1400, sorry. Yeah, this is the minimum, and this is the pure, okay? 1600 is the pure calcium carbonate, and this is the eutectic, this is the thermal divide, and this is the eutectic. So, huge difference, okay? Approximately 1000 degrees C. If we move to magnesium, the same diagram, I took that from Ellis and Wiley. Okay, this was at higher pressure, but what I want to show you is that this point here is expected to be at 1200. Okay, so apparently the effect of H2O is not as big as in the calcium system. Okay, so it's much or is reduced. It's definitely reduced. And if we have this, we can have schematically a situation like this. Okay, so if this is a simplified sketch, okay, probably most of you in petrological, in introductory books in petrology, usually it's turned 90 degrees. Okay, this is an X, and this is temperature. Okay, obviously this now is on the X-axis is temperature. So what happens is that if this liquidus line is displaced only by, I don't know, 100 degrees C, and this is displaced by 700 degrees C, simply because of geometrical relationship, you have a shift of this point toward calcium. Okay? So, and I think the reason for that, so I think this is the basic, this is a very simple geometrical relationship. It is the basic principle for moving the composition of carbonatic liquids toward calcium carbonate simply by adding H2O, just because of that. Because I mean, I don't know why. It's so important, H2O, for calcium, but not for magnesium. So basically, we have this. So again, as I told you, we have basically this field. This field, you can so if you have epidote or aragonite, etc., at 850, 900 degrees, you can generate again, as I showed you, you can generate this kind of liquid by destabilizing epidote. But from a theoretical, I mean, simply from a geometrical point of view, it's very interesting that what I showed you before can be explained if you don't have H2O available. Okay, let's imagine that you cannot flush your sedimentary material with H2O, and you have only hydrous phases destabilizing. Okay, many people love the so-called fluid absent melting. Is very popular for micas. Phengite fluid absent melting, biotite fluid absent melting. Okay, here we can have zoisite fluid absent melting. So we can generate our hydrous carbonatitic liquid by zoisite fluid absent melting. But from topology, if we make a Schreiner-Macher analysis, we can expect that at higher pressure, we could have also lawsonite fluid absent melting. Nobody did experiments, and obviously nobody would consider lawsonite as a magmatic phase. Huh? So it sounds pretty strange, but on principle it is possible. So we should run experiments in this region, because at 8-9 GPa, lawsonite is still stable. It should be stable at this temperature. And if this is true, we should re-intersect the solidus in this region here. And that would be quite interesting, especially for the behavior of some trace elements, etc. Because lawsonite is very popular for people doing this kind of stuff. Okay, so then if we, the basic, so what happens when we have this kind of hydrous carbonatitic liquid? This kind of liquid can mix with a Harzburgite. So this is a pseudo section I computed in a, okay, with some assumption, obviously. So I'm not going to discuss the assumptions. So basically, so this is the slab, 900 and 4.2 GPa. This is the mantle wedge, for instance, 1200, 2.5 GPa. So this is the gradient, okay, in pressure and temperature. So you go up in pressure, you go up, to shallower levels, and you increase the temperature. And here you have the mixing between a liquid, or anyway a component. This is rich, that is similar to the one I showed you before in terms of composition. Here is the Harzburgite, and what I want to tell you simply is that you lose orthopyroxene, okay? So you consume soon orthopyroxene, you generate a wehrlite. So there is a large field for garnet clinopyroxene, so a large field for wehrlite, and up there you have spinel. So basically you enlarge the stability of spinel for this kind of wehrlite at 2.8 GPa, which is a pretty high pressure for a spinel. Okay, so this is what we would expect, is that we consume orthopyroxene. Okay, and so now I'm running probably too long, but just give me 10 minutes to show you this very nice example from the Northern Andes. Okay, I will show you a very nice example from the so-called granatifera tuff in the Mercaderes area. The granatifera tuff was deposited in the southern portion of the so-called northern volcanic zone. Here the Nazca plate is subducting. There is a slab here more on the north, so we are in the southern region of the subduction systems according to this reconstruction by Syracuse. And the nice thing, really nice thing in this case study is that we have this 504 DSDP site, and you cannot see what is here, but all of these symbols is nanofossil ooze, nanofossil chalk, limestone. Okay, all of that is White Cliff of Dover. So there is a lot of calcium carbonate deposited here. Hundreds of meters of calcium carbonate go down. Okay, so this is the granatifera tuff. Typical pyroclastic product. Actually, they don't know where it comes from. There is no more central volcano, as far as I know, that is a clear origin for this pyroclastic flow. The extraordinary thing is that this is the one of the first sketch reconstruction by Weber in 2002. And there is the granatifera tuff contain plenty of xenoliths that sample all of the lithologic section crust to mantle. Okay, so you can find in the xenoliths gneisses, hornblende-rich rock, gabbro, larzolites, whatever kind of rock you want. Is sampled by the xenoliths in the Mercaderes stuff, the granatifera tuff. And among these xenoliths, you have these fantastic rocks. They are, as you can see here, they are white with the pink and green spots, crystals inside. Okay, so the bulk composition, the wool rock composition of this product is obviously. It's extremely rich in calcium, compared to, okay. Extremely rich in calcium because this white stuff is calcium carbonate. Not only calcium carbonate, we show you what is there. And if you look at the magnesium number, it's 87. And the other sample are all, I mean, most of them between 87 and 91. So the magnesium number is typical for a mantle xenolith, okay? It shows extraordinary textural features. Probably, okay, you have orthopyroxene, cyanopyroxene, and garnet. In most cases, olivine is relatively rare. So they are basically pyroxenites with a matrix composed of different carbonates, okay? So the most extraordinary, I think, are these perfectly euhedral sector zone dolomite that are very unusual in, for instance, in metamorphic rocks. Okay, so we have this sector zone with very delicate feature, as you can see here. These very delicate features shows probably a growth where a liquid was present, and with an oscillation of the chemical potential of the different components during growing. And this dolomite is in a calcium carbonate ground mass, but this ground mass also contain other minerals that I will show you. And as you can see here, both orthopyroxene and garnet appears to be dissolved, and you can see here these lobe and cusp features, okay, all around this sort of bubble. So we typically interpret this kind of textural features as a result of dissolution of orthopyroxene, dissolution of garnet in favor of a liquid. And another extraordinary feature is that in this ground mass we have perfectly euhedral aragonite crystals. Okay, very beautiful. Okay, and these big aragonite crystals in a sort of mantle xenolith are embedded in a hydrous phase, now sepiolite or paligorskite. So a hydrous phase. And when we compare this kind of, and this is true also for the other carbonates, in other places we can see this sort of oscillatory zoning in carbonate, and these carbonates are embedded in, and again, this hydrous phase. All of these features are very unusual. Unusual for a metamorphic rock, are unusual for a magmatic rock, are unusual for most rocks, other than for kimberlites. So the strange thing is that if we look in some kimberlites, we have basically the same. These are two kimberlites. For instance, this is koala, this is lac de grasse, and in kimberlites we can observe this globular or rhythmic oscillatory zoning of carbonates, and usually in kimberlite, because of their composition, the hydrous phase is a serpentine. Usually it's not a chloride, it's not, because of the magnesium content, the composition of these hydrous phases is serpentine. Okay? So in our rock, we can also see that in many cases there is a secondary clinopyroxene that appears to be produced by veining, and then again we see some features that might represent a dissolution process. Okay, so if we look at the mineral chemistry, this kind of rock contained, I would like simply to stress that the garnet is extremely enriched in pyrope component. Orthopyroxene can go up to 12% weight percent of alumina, which is pretty high. I mean, this kind of feature point to an original condition at pretty high temperature for this kind of rock. So the primary of, if we can call that in this way, the primary assemblage point to a high temperature condition, and then we have, on the contrary, we have the precipitation of carbonates. And the only way I can show you that the only way you can get the coexistence of calcite, aragonite, and oscillatory zoning between two dolomites, you could do that only in a range in the, something like between 1,000 degrees C, not higher, because then you don't have immiscibility. Okay, you cannot. I mean, you should have a single magnesium calcite. You cannot produce both. I mean, actually, 3 kind of carbonates. Okay, so basically, what happens is that probably we have a mantle wedge. So the primary mineralogy with garnet, orthopyroxene, primary clinopyroxene is here in the order of 3 GPa at 1300, 1400 degrees C, and then this is entrapped in the downwelling flow of the subducting slab and is fluxed by hydrous carbonatitic liquid with calcium-rich hydrous carbonatitic liquid, and this metasomatic agent, adding carbonates, adding water, produces the orthopyroxene. It causes the orthopyroxene dissolution as expected. And this orthopyroxene dissolution, which is very clear here, for instance, you see again, this lobe and cusp is completely dissolved by the carbonates around, okay? And this kind of orthopyroxene dissolution was proposed to drive the fast ascent of kimberlites by Russell et al. In a paper published in Nature in 2009. So the idea is that the dissolution of orthopyroxene in the silicate, in a carbonatitic melt, causes an enrichment in silica and then exsolution of CO2. And this CO2, obviously because of volume expansions, drives the fast ascent of kimberlite to the surface. And maybe this is the same mechanism we have here in the Andes, and this is probably why it's such a unique case for the conservation of the evidence of this hydrous carbonatitic liquid. So to conclude, I would like to stress that there is a large variety of subducted material, and at least part of this material is hydrated, carbonated, and enriched in calcium. So I'm a fan of calcium. Hydrous carbonatitic liquid should be ubiquitous, a relatively warm subduction zone if calcium is provided to the system. The liquids are calcium enriched. They are expected usually to generate wehrlite and eventually enlarge the stability of spinel as a byproduct of this process. But obviously, usually it's difficult to sample this kind of material, okay? So exceptionally sample if there is a process that similar to what we can observe in some kimberlite, where orthopyroxene dissolution favor the exsolution of CO2 as a gas propelling the ascent. Okay, thank you. for your attention. Yes, right. They are relatively, actually, they are relatively ubiquitous. I think that because in the experiments where the acidic activity was relatively low, I got corundum plus whiskers. And whereas when you have when you observe the precipitation of silica globules, obviously you have no corundum, but the whiskers are still there. So I don't know if you get, I mean, apparently there is, if there is aluminum, you precipitate this kind of feature. But yes, probably we also have to play with aluminum, not only with silica activity. Yeah. How much? Andradite. Yeah. Actually, these are, I mean, Israel is in any case, as far as I remember, is in the order of 10%. It's relatively low because these are formed, in any case, before the metasomatic process, okay? Because also garnet appears to be dissolved as well. So we have actually, we observe the precipitation of spinel after the process. Okay.
So the water depresses the calcite temperature to more than 1,000 degrees. Why is that? In silicates, we know why it is. It's all about solution mechanisms and all that. But carbonatite and carbonate is a different beast. Moreover, in magnesite volume, you have smaller depression.
To be honest, I don't know. I don't know why there is such. I mean, it is possible that the original experiments by Pete Wiley, everything was. The characterization was optical. So maybe it's too extreme, but I'm definitely convinced that anyway, between 850 and 900. For sure, you have this kind of feature, and for sure for magnesium is not so extreme. So, but no, I don't have the idea of the physical meaning of the physical reason for that. Maybe Dionysius. Thank you. I would like to ask you.
I don't know the answer.
Because usually, molten salts are assumed to be relatively simple, and so it's, they're just molten salts. So why they are so different?
So, and, we're going to have lunch next door.
Hi, Andrea.
Stefano, good to see
How are you
you.
doing?
Yes, I know you have a busy schedule today, but I wanted to say hello.
Yeah.
I know you're talking.
Thank you for
Craig later.
coming.
Oh, my pleasure.
This is
Not too deep, not too mineral physics here.
No, this is a great topic for this audience, I'll tell you.
Also some rocks.
Also, I love natural samples, and people always cite these old Wiley papers, and I forgot it was optical determination.
Everything at the microscope.
I think I'm on your schedule for 4:30.
Yeah,
I have
right.
A number of questions about your talk, but also a number of other things to discuss as well.
Me as well.
Good. And I'll join you for lunch just
Sure.
now. I think that was great.
Great.